2,000 years ago, Roman engineers pulled off something that would make modern construction crews scratch their heads in amazement. They built massive concrete structures underwater that didn't just survive, they got stronger over time. We're talking about seawalls and harbour breakwaters that are still standing today, laughing in the face of hurricanes, earthquakes, and 20 centuries of pounding waves. Picture this. You're a Roman engineer tasked with building a harbour in the middle of the Mediterranean. No scuba gear, no modern diving equipment, and definitely no underwater concrete pumps. Just you, your crew, and a recipe for concrete that somehow worked better underwater than it did on dry land. Sounds impossible, right? Well, the Romans didn't just make it work. They turned it into an art form that we're still trying to figure out today. Here's what's really wild about this whole story. Modern marine concrete starts breaking down after about 50 years of battling seawater. Salt water is basically concrete's worst enemy. It eats through the stuff like acid through metal. But Roman concrete? It's been sitting underwater for 2 millennia, and it's still getting stronger. Scientists have been studying this stuff for decades, and what they've discovered will blow your mind. The secret ingredient wasn't some mystical Roman magic. It was volcanic ash. Specifically, a type called pozzolana that came from around Mount Vesuvius. The same volcano that buried Pompeii also provided the Romans with the key to underwater construction that would last longer than most civilizations. Talk about finding a silver lining in a volcanic disaster. But before we dive into the chemistry that made this possible, make sure to hit that subscribe button and give this video a like. And definitely drop a comment letting me know what you found most interesting about Roman engineering. I read every single one, and they helped me figure out what topics to cover next. Now, let's talk about just how massive these Roman harbour projects really were. The harbour at Caesarea, built by King Herod around 22 BC, had breakwaters that stretched over 1,500 feet into the Mediterranean. That's like building 5 football fields worth of concrete structure underwater, using nothing but muscle power, wooden tools, and some seriously clever engineering. The entire project took about 12 years to complete and required moving roughly 24,000 cubic meters of concrete underwater. That's enough to fill 10 Olympic swimming pools. What made Roman harbour construction so remarkable wasn't just the scale, it was the precision. These weren't just random piles of rocks thrown into the water. Every Roman harbour was designed with mathematical precision, taking into account wind patterns, wave action, and the specific geology of the seafloor. Roman engineers were basically ancient marine architects who understood fluid dynamics better than most people understand their own smartphones. The planning phase alone was a masterpiece of ancient engineering. Roman surveyors would spend months studying a potential harbour site, mapping underwater topography, measuring seasonal wave patterns, and calculating the optimal angles for their breakwaters. They knew that a harbour wall built at the wrong angle wouldn't just fail. It would actually make wave conditions worse, turning what should have been a safe harbour into a ship-destroying nightmare. Here's where it gets really fascinating. Roman engineers discovered that curved breakwaters worked better than straight ones. Instead of fighting the waves head-on, these curved walls redirected wave energy, dissipating it harmlessly instead of creating dangerous rebounds. It's the same principle that modern harbour designers use today, except the Romans figured it out through trial and error 2,000 years ago. The site preparation was like an underwater archaeological dig in reverse. Teams of divers, the Romans called them urinatores, would clear the seafloor of any loose material, creating a level foundation that could support massive concrete structures. These divers worked without any breathing apparatus, holding their breath for minutes at a time, while moving rocks and positioning guide stakes on the ocean floor. Once the site was prepared, the real magic began with something called a caisson. Think of it as a giant wooden box designed to be floated into position and then sunk exactly where they wanted to build. These caissons were engineering marvels in their own right, double-walled wooden structures that could be precisely positioned, then filled with ballast to sink them to the sea floor. The carpentry work alone was incredible. Roman shipwrights would construct these massive floating boxes using techniques that wouldn't look out of place in a modern boatyard. Every joint had to be waterproof, every measurement precise, because once that caisson was in position on the seafloor, there was no moving it. Get the placement wrong, and you just created the world's most expensive underwater obstacle. But here's what really separated Roman engineers from everyone else. They figured out how to pour concrete underwater. Not just any concrete, but concrete that would actually set properly while submerged in seawater. This was like solving a puzzle that had stumped every other civilization for centuries. The process started on land with lime production. Roman workers would burn limestone in massive kilns, creating quicklime that would then be carefully slaked, mixed with water, to create lime mortar. But the real secret weapon was that volcanic ash, pozzolana, which came from deposits around Mount Vesuvius and other volcanic regions throughout the Roman Empire. The pozzolana wasn't just any volcanic ash. It had a specific chemical composition that made it react with lime in the presence of seawater. When these three ingredients came together underwater, they created a chemical reaction that formed crystals similar to natural rock formations. Instead of the concrete weakening over time like modern concrete does, these crystals actually made the structure stronger and more resistant to seawater damage. The logistics of getting all these materials to a construction site in the middle of the ocean were mind-boggling. Imagine coordinating the delivery of tons of lime, volcanic ash, and stone aggregate to a floating construction zone where everything had to be mixed and placed while boats rocked in the waves. Roman project managers were dealing with supply chain challenges that would make modern logistics experts nervous. The actual concrete mixing happened on barges floating directly over the construction site. Workers would combine the lime mortar with pozzolana in specific proportions, usually about 1 part lime to 2 parts volcanic ash. Then came the aggregate, chunks of volcanic rock called tuff, broken pottery, and stone offcuts that would give the concrete its bulk and strength. What happened next was like an ancient version of extreme construction. Teams of workers on barges would lower this concrete mixture through the water column down into the wooden caissons on the sea floor. The divers below would guide the placement, making sure the concrete filled every corner of the caisson and didn't leave any air pockets that could weaken the structure. The Romans had figured out that their concrete actually worked better underwater than it did on land. The seawater didn't weaken the mixture. It was an essential ingredient in the chemical reaction that made the whole system work. While other civilizations were still trying to keep water away from their concrete, the Romans were embracing it as part of the construction process. The setting time was crucial. Roman concrete needed about 48 hours to reach initial strength, during which time the structure was vulnerable to wave damage. But once it set, something remarkable happened. Instead of slowly deteriorating like modern concrete, Roman underwater concrete continued to strengthen over the decades and centuries that followed. The construction crews worked in carefully coordinated shifts. Carpenters maintained the wooden caissons and barges. Barge crews positioned materials and moved equipment. Divers guided underwater placement, and masons prepared for the above-water finishing work that would come later. Everyone had to work together like a perfectly synchronized underwater ballet. Except this ballet involved tons of concrete and the constant risk of drowning. The most dangerous part wasn't the diving or the heavy lifting. It was timing the pours with the weather. Roman engineers had to become amateur meteorologists, reading wave patterns and wind conditions like their lives depended on it, because honestly, they did. One badly timed concrete pour during rough seas could destroy weeks of work and potentially kill half the crew. These guys were playing construction roulette with Mother Nature, and the stakes couldn't have been higher. What's really impressive is how they handled quality control underwater. Modern concrete inspectors can walk around a job site with fancy equipment, taking samples and running tests. Roman quality control happened 40 feet underwater with nothing but human judgment and experience. The master divers could actually feel the consistency of the concrete as it was being placed, using their hands to detect air bubbles or weak spots that could compromise the entire structure. The concrete mixture itself was like a carefully guarded recipe. Different harbours use slightly different proportions based on local conditions and available materials. The harbour at Kosa used a mix that was roughly 2 parts volcanic ash to 1 part lime, with heavy aggregate making up about 60% of the total volume. But at Portus, near Rome, they adjusted the recipe to account for different wave conditions and seafloor geology. Here's where Roman engineering gets almost supernatural. They discovered that certain types of seawater actually improved their concrete's performance. Water with higher concentrations of dissolved minerals created stronger chemical reactions with the pozzolana. Some Roman harbours were deliberately built in locations where underground springs mixed fresh water with seawater, creating the perfect chemical cocktail for their concrete to thrive. The aggregate selection was another stroke of genius that modern engineers are still studying. Romans didn't just throw random rocks into their concrete. They chose specific types of volcanic stone that would bond perfectly with their lime pozzolana mixture. Tough, the lightweight volcanic rock they preferred, had just the right porosity to allow the chemical reactions to penetrate throughout the entire concrete mass. It was like they had figured out the molecular structure of concrete 2,000 years before anyone knew what molecules were. But the real magic happened during the curing process. While modern concrete reaches its maximum strength in about 28 days, Roman underwater concrete kept getting stronger for decades. Scientists studying samples from ancient harbours have found that the concrete was still developing new crystal structures after 50 years of submersion. It's like the Romans accidentally invented self-healing concrete that got better with age. The construction sequence was a masterclass in project management. Once the caisson was filled with concrete and had reached initial strength, crews would begin the above-water finishing work. This is where the true artistry of Roman harbour construction showed itself. The rough concrete core would be faced with carefully cut stone blocks, creating smooth walls that could withstand both wave action and the constant scraping of ships mooring against them. The stone facing wasn't just decorative, it was a critical part of the structure's long-term durability. Roman masons would select stones that complemented the concrete's properties, often using the same volcanic materials that went into the concrete mixture. The joints between stones were filled with the same pozzolana mortar, creating a seamless integration between the facing and the core structure. Installing these facing stones while working from boats was like trying to build a jigsaw puzzle while riding a mechanical bull. Each stone had to be precisely positioned and perfectly level, despite the constant motion of the work platform. Roman stonemasons developed specialized tools and techniques for this marine construction, including adjustable lifting devices that could compensate for wave motion during placement. The finishing touches were where Roman harbours really showed their sophistication. Iron rings and bollards were set into the concrete while it was still workable, creating permanent mooring points that would last for centuries. These weren't just functional elements, they were often decorated with carved reliefs and inscriptions that proclaimed the harbour's importance and the glory of its builders. Some harbours featured massive lighthouse foundations, built using the same underwater concrete techniques. The famous lighthouse at Alexandria may have been built using Roman concrete methods, creating a foundation so solid that parts of it are still visible on the seafloor today, over 1,500 years after the lighthouse itself collapsed. The Romans also figured out how to create underwater concrete structures with complex shapes. They weren't limited to simple rectangular caissons. They built curved walls, angled breakwaters, and even underwater chambers that could serve as storage spaces or workshops. The harbour at Baiae featured underwater concrete vaults that were used as fish ponds and storage areas, demonstrating that Roman engineers could create habitable spaces below the waterline. Quality control extended to regular maintenance schedules that would make modern harbour authorities jealous. Roman harbour masters kept detailed records of structural inspections, noting any signs of settlement, cracking, or marine growth that might affect the structure's performance. They had developed techniques for underwater repairs that could extend a harbour's service life indefinitely. The economic impact of these harbours was staggering. A properly built Roman harbour could handle ships carrying up to 1,200 tons of cargo, massive vessels by ancient standards. The harbour at Portus could accommodate over 180 ships simultaneously, making it one of the busiest ports in the ancient world. The concrete construction techniques made these massive facilities economically viable by eliminating the constant rebuilding that plagued harbours built with traditional materials. But perhaps the most remarkable thing about Roman underwater concrete wasn't its strength or durability. It was how it enabled the Romans to build harbours in locations that would have been impossible with any other construction method. They created safe harbours on exposed coastlines, in areas with difficult geology, and even in locations where the seafloor was too soft to support conventional stone construction. The harbour at Caesarea Maritima was built on a sandy bottom that would never have supported a traditional stone breakwater. The Roman concrete foundation spread the load over such a large area that the structure remained stable despite being built on what was essentially underwater quicksand. It's like they figured out how to build skyscrapers on beach sand 2,000 years before anyone invented modern foundation engineering. This revolutionary construction technique didn't just change how Romans built harbours, it transformed their entire approach to marine engineering and opened up possibilities that would influence construction methods for centuries to come. The Romans took this concrete technology and ran with it like they'd discovered fire all over again. But here's what really blew my mind when I first learned about this. They didn't just stumble onto this discovery by accident. Roman engineers systematically tested different volcanic ash sources across their empire, creating what was essentially the world's first materials science laboratory. They had teams of specialists whose only job was to travel from volcanic region to volcanic region, collecting samples and testing their properties. These guys were like ancient concrete detectives, figuring out which volcanic deposits produce the best underwater concrete. The pozzolana from the Bay of Naples was considered the gold standard, but they found workable volcanic ash as far away as Germany and North Africa. What's absolutely wild is how they figured out the mixing ratios without any of our modern testing equipment. No concrete strength meters, no chemical analysis, just trial and error on a massive scale. Roman engineers would build test structures, let them cure for months, then literally try to destroy them to see how strong they'd become. It was like the ancient equivalent of a demolition derby, except they were testing building materials instead of cars. The quality control standards they developed were insane by ancient standards. Every batch of concrete had to be mixed according to strict specifications that were written down and passed between construction crews. They had what we'd recognize today as standard operating procedures, except theirs were carved into stone tablets instead of printed on safety manuals. But the real genius shows up when you look at how they adapted their concrete recipes for different environments. Harbours in the rough Atlantic got a different mix than ports in the calmer Mediterranean. They figured out that water temperature, salinity levels, and even the types of marine life in an area affected how their concrete would perform over time. The Romans discovered that their concrete actually got stronger in areas with more aggressive wave action. The constant pounding of waves drove seawater deeper into the concrete matrix, accelerating the chemical reactions that made the structure more durable. It's like they accidentally invented self-improving construction materials that fed off the very forces trying to destroy them. Some of the most impressive Roman harbour construction happened in places where the weather tried its best to kill everyone involved. The harbour at Dover was built during some of the worst winter storms on record. with crews working in conditions that would shut down modern construction sites for weeks. These guys were basically construction superheroes who treated hurricanes like a minor inconvenience. The diving operations alone were death-defying by any standard. Roman divers regularly worked at depths of 60 feet or more, holding their breath for up to 4 minutes while positioning concrete and adjusting underwater formwork. They developed breathing techniques that wouldn't look out of place in a modern freediving competition, except they were doing it while wearing heavy work clothes and manipulating construction materials. The logistics of coordinating these massive underwater construction projects makes modern project management look simple. Roman harbour construction required dozens of specialised barges, hundreds of workers, and precise timing that had to account for tides, weather, and seasonal shipping schedules. One delay in material delivery could shut down an entire harbour construction project for weeks. They even figured out how to work around marine life. Roman engineers learned to time their concrete pours to avoid spawning seasons when fish populations might interfere with construction. They developed techniques for temporarily relocating dolphins and seals that might otherwise disrupt diving operations. It's like they were running an ancient version of environmental impact assessment. The speed of Roman harbour construction was absolutely ridiculous. The harbour at Leptis Magna was completed in just 18 months, despite requiring over 15,000 cubic metres of underwater concrete. That's faster than most modern marina construction projects, and they were doing it with hand tools and muscle power. Roman construction crews worked in shifts around the clock, with torches providing light for nighttime concrete pours. But here's what really separated Roman harbour engineering from everyone else. They built their structures to handle disasters that wouldn't happen for centuries. Roman harbours were designed to survive earthquakes, tsunamis, and storm surges that might only occur once every few hundred years. They were basically building for the apocalypse before anyone knew what apocalypse meant. The harbour at Alexandria survived a massive earthquake in 365 AD that destroyed most of the city's buildings. The concrete breakwaters remained intact while everything else around them crumbled. Roman engineers had somehow figured out how to make concrete that could flex with seismic forces instead of shattering like brittle stone. The chemical reactions happening inside Roman concrete were like having a construction crew that never stopped working. Even after the initial setting was complete, the lime and pozzolana continued reacting with seawater to create new crystalline structures. Scientists have found concrete samples that were still actively forming new crystals after 1,500 years underwater. Modern researchers trying to reverse engineer Roman concrete have discovered that the volcanic ash they used contained trace elements that acted like catalysts, speeding up beneficial chemical reactions while inhibiting the processes that cause normal concrete to deteriorate. It's like they accidentally created concrete with built-in preservatives. The Romans also figured out how to create concrete with different properties in different parts of the same structure. The foundation sections used a mix optimized for maximum strength and chemical resistance, while the upper portions used lighter aggregates that provided better workability for the stonemasons who would be finishing the surface. Some Roman harbours featured underwater concrete structures with internal drainage systems that prevented water pressure from building up inside the walls. These drainage networks were so sophisticated that modern engineers initially thought they were looking at much later additions to the original Roman construction. Turns out the Romans had figured out hydrostatic pressure management 2,000 years before anyone invented the math to calculate it properly. The construction equipment they developed specifically for underwater concrete work was ingenious in its simplicity. Roman engineers created specialized concrete buckets with controlled release mechanisms that could deliver perfectly measured amounts of concrete to specific underwater locations. The buckets were designed to sink at exactly the right speed, allowing divers time to guide them into position before the concrete was released. They even developed underwater concrete pumps, sort of. Roman engineers created long canvas tubes that could be filled with concrete mixture and then squeezed like giant toothpaste tubes to force the concrete into tight spaces between rocks or into narrow formwork. It was crude by modern standards, but it worked well enough to build harbours that are still standing today. The precision of Roman underwater construction was absolutely mind-blowing. Some harbour walls were built to tolerances of less than an inch over distances of hundreds of feet. They achieved this accuracy using nothing but string lines, lead weights, and an incredible amount of skill. Roman master builders could eyeball measurements that would require laser levels today. But the most impressive thing about Roman harbour concrete wasn't its strength or durability. It was how they managed to make it economically viable on such a massive scale. The concrete mixture used locally available materials wherever possible, reducing transportation costs that could have made these projects financially impossible. Roman engineers developed standardized concrete recipes that could be adapted to use whatever volcanic materials were available locally. A harbour in Spain might use different volcanic ash than one in Turkey, but both would follow the same basic principles and achieve similar performance characteristics. It was like having a franchise system for ancient concrete technology. The training programs they developed for concrete workers were surprisingly sophisticated. Roman construction crews included specialists who did nothing but mix concrete, others who specialized in underwater placement, and master craftsmen who could judge concrete quality by feel and appearance. These skills were passed down through generations of builders, creating a knowledge base that lasted for centuries. Some of the most impressive Roman harbour construction happened in locations that seemed completely impossible. The harbour at Cosa was built on a rocky coastline where the seafloor dropped off into deep water just a few feet from shore. Roman engineers had to create artificial foundations in water over 100 feet deep, using concrete caissons that were essentially underwater skyscrapers. The environmental impact of Roman harbour construction was surprisingly minimal for such massive projects. The concrete they used was made from natural materials that didn't harm marine ecosystems, and many Roman harbours actually became artificial reefs that supported thriving underwater communities. Modern marine biologists studying ancient Roman harbours have found some of the most diverse underwater ecosystems in the Mediterranean, growing on 2,000-year-old concrete structures. Roman concrete technology was so advanced that when the empire fell, the knowledge of how to build underwater concrete was lost for over 1,000 years. Medieval builders tried to recreate Roman harbour construction techniques, but failed repeatedly because they didn't understand the chemistry behind the volcanic ash mixtures. It wasn't until the 18th century that engineers began to rediscover the principles that made Roman underwater concrete so effective. The legacy of Roman harbour engineering extends far beyond just construction techniques. These harbours enabled trade networks that connected 3 continents, supported cities with populations in the hundreds of thousands, and created economic prosperity that lasted for centuries. The concrete technology that made it all possible represents one of the most significant engineering achievements in human history. Today's concrete engineers are still learning from Roman techniques, trying to recreate the self-healing properties and extreme durability that Roman builders achieved with simple natural materials. Some modern experimental concretes incorporate volcanic ash specifically because researchers are trying to replicate the chemical reactions that made Roman structures so incredibly long-lasting. But perhaps the most remarkable thing about Roman underwater concrete is that it represents a completely different philosophy of construction, building not just for immediate needs, but for geological timescales that stretch far beyond any individual human lifetime. The scale of Roman ambition becomes clear when you look at the numbers behind their most ambitious harbour projects. The port complex at Portus, which served Rome itself, required moving over 85,000 cubic metres of concrete underwater. That's enough material to build a modern shopping mall, and they did it all without a single diesel engine, hydraulic crane, or concrete mixer truck. What makes this even more incredible is how they solved the problem of concrete segregation. Anyone who's ever watched concrete being poured knows that if you don't keep it moving, the heavy aggregate settles to the bottom while the lighter cement floats to the top. Underwater, this problem gets 10 times worse because you're fighting gravity, water pressure, and wave action all at the same time. Roman engineers figured out that the key was controlling the descent speed of their concrete. They developed these ingenious funnel systems that could regulate how fast the mixture dropped through the water column. Too fast, and the concrete would hit the bottom like a bomb, scattering aggregate everywhere. Too slow, and the lime mortar would wash away before it reached the construction zone. The funnels themselves were works of art. Made from waterproof leather stretched over wooden frames, they could be adjusted on the fly to compensate for changing conditions. Roman concrete crews became masters at reading the water. They could tell just by watching the surface whether their concrete was dropping at the right speed or if they needed to make adjustments. But here's where Roman ingenuity really shows. They discovered that adding chopped seaweed to their concrete mixture actually improved its underwater performance. The seaweed fibers acted like primitive reinforcement, preventing the concrete from cracking as it cured. Modern fiber-reinforced concrete uses synthetic materials to achieve the same effect that Romans got from kelp they pulled out of the ocean. The timing of these operations required coordination that would impress modern construction managers. Roman harbour projects ran like military campaigns, with detailed schedules that accounted for everything from tide tables to the lunar calendar. They knew that concrete poured during certain moon phases would cure differently, and they planned their construction sequences accordingly. The most dangerous part of the entire operation was the moment when concrete met seawater for the first time. Get the chemistry wrong, and instead of setting into solid rock, the mixture would dissolve into expensive underwater soup. Roman engineers developed test procedures that could predict how their concrete would perform before they committed to a full pour. They'd lower small samples of their concrete mixture to the seafloor and retrieve them after different time intervals, checking the consistency and strength development. It was like having a laboratory 40 feet underwater, except their lab equipment consisted of ropes, baskets, and the skilled hands of divers who could judge concrete quality by touch alone. The pressure management during large concrete pours was absolutely critical. When you're placing hundreds of tons of concrete into a confined space underwater, the hydrostatic forces can blow apart your wooden forms like they're made of paper. Roman engineers developed pressure relief systems that could safely handle these forces without compromising the structural integrity of their work. Some of their larger caissons included built-in drainage channels that allowed trapped air and excess water to escape as the concrete was being placed. These channels were precisely calculated to prevent blowouts while ensuring that the concrete could flow into every corner of the form. It's the kind of hydraulic engineering that requires an intuitive understanding of fluid dynamics that most modern engineers would struggle to match. So the next time you're stuck in traffic complaining about a pothole that's been there for 6 months, remember that Roman engineers built underwater concrete structures that have been getting stronger for 2,000 years. They turned volcanic ash and seawater into construction materials that outlasted their entire civilization. While we're still figuring out how to make concrete last 50 years without falling apart, the Romans accidentally created the ultimate building material using nothing but limestone, volcanic ash, and an incredible amount of trial and error. Their harbours are still standing today, quietly mocking our modern engineering while providing homes for Mediterranean sea life that's probably been living there longer than most countries have existed.